All right, crew, your last section for Unit 2, States of Matter. We're going to talk about the kinetic molecular theory in this section. So essentially, we've come up with all these laws that apply to gases, and now we're going to develop a theory that helps to explain why these laws occur. All right, the kinetic molecular theory has 5 points. And I got to say, this is probably my least interesting slide of the entire semester, so I apologize. You just got to write a lot. Okay, particles of a gas. What are they doing? Well, the kinetic molecular theory says that these particles are in constant motion, moving in straight lines until they collide with another particle or a wall of the container in which they're enclosed. So they do not act like curveballs. There are no curveballs, so they are in straight lines until they collide with another particle or a wall of the container in which they're enclosed. So then they'll collide with the particle or container, and they'll ricochet back and forth, and they'll keep kind of bouncing around in that particular container. All right, 2 for the kinetic molecular theory. They experience elastic collisions. So what that means is that when they run into each other, if 2 particles run into each other, one particle doesn't give its energy to the other particle. If that would happen, then we would see the particle that lost its energy eventually run down. It would actually lose energy. And after a while, it would lose so much energy that it wouldn't be able to move anymore. And it would fall down to, the gravitational pull, the Earth. And we don't see that. Molecules don't just fall out of the air. Oxygen is heavier than nitrogen. So we don't see the nitrogen molecules running into the oxygen molecules, losing their energy, and then falling down to the air, to the ground. That certainly doesn't happen. So when the particles run into each other, they do so elastically, and they kind of reverberate back and continue to move. So let's say if we get this one going this way and this one going this way, boom, they'd run into each other, and then they'd be going, one would go that way and one would go that way, and they don't lose their speed. Okay, that's the idea. Number C, they do not stick to other particles. So we don't have 2 particles that are flying through the air, and one of them comes this way, and the other one comes this way, and they're coming at each other like so and like so, and we do not have this going on. So the sticking of particles to form like one massive particle. If we ever do get these particles to combine with each other, that's due to a chemical reaction. And we'll talk about that later on, obviously, in the semester. D, the speed of the particles is related to their temperature. I think we know this. The faster particles go, the higher the temperature is going to be. And then finally, E, the pressure of the gas is related to the frequency and the impact of the collisions of the gas on the container itself. So the more collisions there are on the container, the higher the pressure is going to be. And the harder those collisions are with the container, the higher the pressure is going to be. So these are theories. This is the kinetic molecular theory that helps us explain a bunch of aspects of gases. It helps us explain why pressures are the way they are, the speeds of gases and how that relates to temperature. It helps us explain volumes of gases and why, we've got enclosed containers, and why volumes stay the way they are. So it gives us a little look into all of those different variables that we've been talking about throughout this entire unit. Now, I'd be remiss to skip out on the opportunity to describe, sorry about my transitions, to describe the difference now between laws and theories. So we've had Boyle's law and Gay-Lussac's law, Charles' law, and the combined gas law. So law, and law. And now today, I'm throwing at you a theory, the kinetic molecular theory. So you might be curious as to wonder, okay, what the heck is the difference? Because you've probably heard theories before and might not actually know what the definition of those are. Well, let's talk about laws first of all. So the laws that we have focused on in this chapter. We've got Boyle, we've got Charles, we've got Gay-Lussac. I'm wondering if anybody has a favorite of these 3. I don't know, I like Boyle's best because he's got really awesome hair. Check him out. Go and Google him. Yeah, seriously, stop the video. Go and check him out. He's got this awesome hair. So the laws are just simply descriptions of observed phenomenon. Okay, so these guys, Boyle, Charles, and Gay-Lussac, were just pretty observant. And Boyle was like, all right, well, I've got this pressure and I've got this volume. Let me go ahead and change the pressure. I bet you I don't even have to do an experiment to figure out what the new volume is going to be. I can just use this handy-dandy little equation. And we prove that in the lab, which is awesome, and it proves that science works, and we love it. So that's a law. He's just describing observed behavior. As this changes, as P changes, and V changes, we can now determine a new P and a new V. Okay? He's not essentially explaining why that happens. He's not explaining why is it that when pressure is increased, volume decreases. He's just explaining that that is the case. All right? So let's think about other laws besides the ones that were in our particular unit. The law of gravity. That is certainly a law. Okay? If Sammy comes into class tomorrow and she picks up Bailey and she drops her, Bailey is going to fall to the ground every single time. If Sammy repeatedly picks up Bailey and continually drops her over and over again, she will continue to fall. If at any point in time she stops falling, levitates, and moves upwards, we all need to be concerned. That just doesn't happen. So gravity is a law, the universal law of gravity is what it's called. And it's our observed behavior. If we drop Bailey or a pencil or an apple or whatever it is we drop, it is going to fall towards the ground. The ground being the earth being the bigger object. Now, why does that happen? There you go. We have observed it. We have kind of defined it. But why does it happen? Well, that is where we get this new term. That is where we get this guy, the theory. Okay? Now, there's a difference between everyday theories that you and your friends have in the hallway and scientific theories. Okay? You might have a theory of like why your best friend is having a really bad day. Well, you know, he broke up with his girlfriend, or he had a bad quesadilla for lunch, or whatever it may be. It might be your theory as to why they're having a bad day. But that is not a scientific theory. That is your own personal theory of that particular issue. Scientific theories are much more grounded in evidence. Okay, so a scientific theory is an explanation of the observed phenomenon, and I'm missing a little bit here to my definition, but I kept it vague for a reason. Some other things that go into scientific theories, you gotta have a ton of evidence, and you have to have a ton of experimentation. So, if I can refine my definition a bit, you got an explanation of the observed phenomenon based on experimentation and evidence, and there's a lot of this stuff. And scientific theories are scrutinized wholeheartedly. Like, think of global climate change. Oh my goodness, it is totally scrutinized. But things like that are very controversial are backed by repetitive positive tests. So we see a global climate crisis. There are tons of tests that repeat these observations. Thus, it becomes a scientifically valid theory. Okay? We understand all these gas laws. We see them happen all the time. So we developed the kinetic molecular theory. And it repeats these tests all the time, so it becomes a scientific theory. Okay? Scientific theories are accepted by the vast majority of the scientific community. Now, there are some people that may go against scientific theories for some reasons. And to be honest with you, when a theory is first proposed, there's a ton of people that typically go against it, and then they try to refute that theory. But if the theory is solid, if it's good, if it stands the test of time, it consistently comes back with positive tests, and it holds true. And the mark of a great theory is that it can be used. It can actually be used to predict outcomes of certain things. Kinetic molecular theory is one of those ideas that can be used to predict outcomes. And let me go back to the previous slide. And look at letter E. It says the pressure of a gas is related to the frequency and impact of the collisions of the gas with the sides of the container in which they are enclosed. That's a theory as to why Boyle's law is what it is. So if we increase the frequency of the impacts, if we put more molecules into our substance, or if we pressurize, if we shrink the volume of our container, so if volume goes down, the pressure will go up. Okay? And so we can use this part of the theory to predict the relationship of Boyle's law and how Boyle's law actually works. And we can do it for a whole bunch of other things. We can do it for evolution. We can predict the evolution of certain species that are evolving on isolated islands on the eastern coasts of Africa, an island you may be aware of called Madagascar. And we can predict things like the actual current pacing of our universe and how it is continually expanding at an ever-accelerated rate by understanding the idea called the Big Bang Theory. And if we understand these theories, we can use them to predict certain outcomes. And that's pretty cool stuff. That's cool science. All right, that's 2.5. That's it for Unit 2. You are done with notes for states of matter.